So hello everyone. So it has been a very long time since I recorded and uploaded a video, and this is usually because I have been really busy with my schoolwork, and yeah. So now I'm back, and I'm just gonna continue making more competition videos. So this video is gonna be about the American Invitational Mathematics Examination, number 2. And the reason I'm doing number 2 and not number 1 is because the number 1 solutions has been released by our problem solving. So if you guys are interested in the AIME I competition, then you guys should probably check out our problem solving's math jam. And obviously I'm doing 2 before Saturday. Actually today's Saturday. Yeah, so before our problem solving's math jam, because I want to present the unique solutions I did it myself. And I'm not going to make any videos on any questions after number 6 because I myself have no idea how to do them, because I only did like 6 questions on this exam, so forgive me for that. And I'm pretty sure I got all these 6 correct because the only questions that I did are these 6 questions, and yeah, and then in total I got 6 marks. So definitely I know I got these correct. So please trust me. So let's move on to the first problem. So the first problem is about so there's a 3. So what is the arithmetic mean? So arithmetic mean of all 3-digit palindromes. So palindromes are basically numbers that are symmetrical visually. So for example, 737, 848. So as you can see, the first digit and the third digit are the same. So as long as this condition is satisfied, it's basically a palindrome. And basically this question is asking for the arithmetic mean. And the arithmetic mean basically means like the average of all of these numbers. So to start with this problem, obviously we want to list some palindromes. So let's start from the lowest 3-digit palindrome, which is 1, 0, 1. And what happens is afterwards, we just want to keep the first digit and third digit the same, and we actually don't really care about the second digit. It's like 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's the same for 202, 202, and 212, and so on. And at the end, the biggest palindrome is 999. And obviously what you can see here is that all the palindromes, if you list them from smallest to largest, it forms an arithmetic sequence, meaning that the common difference between each consecutive palindrome is the same. And in this case, the common difference is 10. So obviously what we can do is we can sum up all of the, we can do an arithmetic sum. And just to make this short, when you're computing the sum of an arithmetic sequence, obviously what you can do is there are 2 formulas for this, and the quickest formula is adding the initial term, so A1, and the final term times the number of terms divided by 2. So in this case, the first term is 101, the last term is 999. How many terms are there? So as you can see, if the first digit and third digit is 1, then there are 10 numbers. And we know that the first digit can be only 1 to 9. It cannot be 0. So 10 times 9 is 90. So 90 divided by 2. And this is the sum. This is the sum. This is not the mean. If we want to find the mean has to be sum divided by the total number of terms, which is 90. So what happens is it becomes the 90 cancels out. So what happens is 101 plus 999 divided by 2. So the final answer is 550. So this question, I would say, is the easiest problem on this exam. And I would say like this is this is a very easy, like I would probably say this is the level of difficulty equivalent to a question before number 10 on the AIMC 12 or even the AIMC 10. So a free mark question, I guess. So number 2 is a geometry problem. I'm gonna try to draw the diagram as accurately as possible. So basically what we have is we have this equilateral triangle with side length of 840. And let's call this ABC. And what happens is there's a parallel line that's intersecting AB at E and AC at F. And there's a line here, BD. And BD is perpendicular to BC, and DF, this line called L, I think, L is perpendicular to BC. Parallel to BC. And then there's another triangle here, and this is called AG. And the property of this is that in the question it's given that AFG, triangle AFG is an isosceles triangle. So what can we actually really get out of this question? Oh, by the way, another condition given is that the area of AFG to triangle BDE is equal to 8 to 9. So what happens is, so we're given these conditions. So we're given that ABC is an equilateral triangle with side length of 840. We're given that AFG is an isosceles triangle. DG is parallel to BC, and BD is perpendicular to BC. And we also know the area ratio between AFG and BDE. So in the question, what we're trying to find is the side length of AF. So how do we proceed with this problem? Well, first of all, we have to understand that we have to make use of every single condition that we have. And the first condition we notice is that DG is parallel to BC, which means that this angle equals to this angle and this angle equals to this angle. Since ABC is an equilateral triangle, this is 60 degrees, 60 degrees, 60 degrees, 60 degrees, and 60 degrees, which means that AEF is also an equilateral triangle. We know that AF and FG is, it's an isosceles triangle. So what happens is the angle FAG is equal to angle FGA. So we know that these two are 30 degrees. And an interesting thing is that EAG, this whole triangle, is actually a 90, 60, 30 degree triangle. So that's very, very interesting. Now let's look at BDE. So BDE is actually another 60, 30, 60, 90 triangle. So what does this really tell us? It tells us that the triangle BDE is similar to triangle GAE. So let's write that down. So triangle GAE is similar to triangle BDE. And how do we actually make use of this? So we need to check what conditions we have not used. So the only condition that we have not used is the area ratio. So what does this really tell us? Well, first of all, we notice that the triangles are similar. Another thing we notice is that AEF is an equilateral triangle, which means that EF is equal to AF and also equal to AE. So what happens is EF is equal to FG. If EF is equal to FG, then F is the midpoint of EG, which means that triangle AFG is what? It's half of the area of AEG. So EAG is equal to 2S AFG. If this is the case, then what we know is that from similar triangles, we know that the side length, so from similar triangles, we know that the side length has to be, the ratio between the side length has to be the square root of the ratio between the areas. So what we can get out of this is that we know that AEG is 2 times of AFG, like in terms of the area. So when we write out the area ratio between EAG and EDB, so EAG we know that it's because before it's 8 to 9, so it's 16 to 9 now. And which means that if we look back here, it means that our side length of DE to EG, so DE to EG is square root of 9 to 16, which is 3/4. But how does this really tell us anything about AF though? So let's set AF as X first. So since AF and FG are equal, so FG is also X. And we know that AEF is an equilateral triangle, so both of these are X. So we know that EG is 2X now. But how's DE any how's it related to X? So if we draw like a rectangle here, we can see that this is very symmetrical. So what happens is DE is going to be, this length is going to be equal to this length because it's symmetrical. So what happens is DE is now equal to 840 minus X over 2. And if we do this, let me just simplify a little bit more. So what happens is we can write out some equations. So 420 minus X over 2 divided by 2X is equal to 3/4. And we should simplify a little bit. And I believe the answer should be 210. Yes, I believe the answer should be 210. So that's what AF is equal to. So do you think this answer is correct? If you think it's correct, then there's something wrong with you. So obviously this is not correct because what happens is I've actually compared a wrong side length. So if you look back to the picture, I compared DE to EG. So DE to EG is obviously not correct because if you look at the triangle formula I wrote, DE should be corresponding to AE. So what happens is 2X shouldn't be 2X, it should be X. And if it's X, then the whole thing completely changes. So let me just erase this. So if it's X, then 3X, then we just do some algebra as usual. And the answer should be 336. Yeah, so that's the correct answer. For number 3, it's a little bit more interesting. So this is where I think it gets a little bit harder and you actually have to think it through. So if we have x1, x2, x3 plus x1, x2, x3, x4 plus x3, x4 plus 5. Equals to something. And how do we, so we're giving a set of 1, 2, 3, 4, 5. So what it's asking is how many permutations there are for each number corresponding to x1, x2, x3, so that the number we get at the end is divisible by 3. So obviously, what we can immediately get from this equation is that we want to do something that's related to modular arithmetic. So how do we really start? So we can first start by writing this equation as equivalent to 0 mod 3. And okay, so now we know 0 mod 3. So what now? One thing you have to notice is that this equation is extremely symmetrical. So what happens is if you can find one condition, then you can times it by 5, and then like you can apply it to different conditions. You'll see what I mean when I go through this problem. Another thing we notice is that in each term, like in these 5 terms, x1, x2, x3, and like the product of 3 numbers, what happens is one number actually appears. Every single number appears exactly 3 times. So as you, for example, let's take x3 as an example. So you can see x3 appears 3 times. x1 also appears 3 times. What does this actually mean? We know that one of the numbers has to be 3. So if there's a 3 inside this term, so for example this term, the whole thing can be divided by 3. So we don't actually care about those terms that can be divided by 3, that are divisible by 3. We want to care about those terms that cannot be divided by 3. So without loss of generosity, let's assume that x1 is equal to 3 now. So what happens if x1 equals to 3? So we see that this term, oh whoops. So we see that this term, and this term, all of them, these 3 terms, let me just change the color. So all these terms are divisible by 3, and we don't really care about them anymore. And all we left is x2, x3, x4 plus x3, x4, x5 equivalent to 0 mod 3. And what happens is we want these 2 terms to add up to 0 mod 3. So what are the possibilities? One possibility is that x2, x3, x4 is 1 mod 3. x3, x4, x5 is 2 mod 3. And vice versa. It's also the same as if you're doing x2, x3, x4 is 2 mod 3, and x3, x4, x5 is 1 mod 3. And now we have to look at the numbers that remain. So we still have 1, 2, 4, 5. So how do we make 1 mod 3? So one way we can do this is obviously by 1, 2, 5. I'm sorry, not 1, 2, 5. Let's say 2, 4, 5. So 2 times 4 times 5 is 1 mod 3. Is there any other combination numbers that produces 1 mod 3? There actually is, and it's let's see 1, 2, 5. 1 times 2 times 5 is also 1 mod 3. So what happens in these conditions is that we know that x2, x3, x4 has to be 2, 4, 5, but we don't really know which one has to be a specific number. But what we know is that x5, which didn't appear in the above term, has to be, so let's say in this case, it has to be 1. So if we look at x3, x4, it has to be 2 of these 3 numbers. And we have to choose these 2 of these 3 numbers to produce 2 mod 3. So let's look at this condition first. So how many terms, how many different combinations can we get for 2 mod 3? So Obviously, if we look at this question, there are, so 4 times, let's see, so 4 times 5 can be an option. What else? 2 times 4 can also be an option. Yeah, so there are 2 options for this case. And if we look back to this condition, we have, if we look back to another case, then we have 1, 2, 5. So obviously the remaining number has to be 4. Yeah, so 4. So how do we produce 2 mod 3? So the way we produce 2 mod 3 is through, let's see. So we can have 1 times 2, or we can have 1 times 5, and 2 times 5 doesn't work. Yeah. So we have 2 options in this case as well. However, we have to remind ourselves that the 2 conditions can be exchanged. So what I mean by this is that 1 mod 3 can be applied to x3, x3, x4, x5, and as well as x2, x3, x4. So we have to times both of these options by 2 actually. So we have 8. And we're actually not done yet because x4 and x5 can also be exchanged. So we have to times 2 again. And this is the total number of conditions when we have x1 equals to 3. And there are a total of 5 choices for like putting a 3. So we have 16 times, this is a little bit messy, sorry. So we have a total of 16 times 5, which is 80. So the final answer is 080. And if you guys think because I'm also very not 100% sure if this question is like, if I solve it the right way. So you guys can tell me if I made any mistakes. So this is like a very, like I didn't think I solved it in the best way possible, but this is how I solved it during the exam. And the 4th question is going to be this question about roots. And I believe this is a relatively easy question. So basically what happens in these 2 questions is that, both of these, so this guy has a root of -20 and this guy has a root of -21. And both of them share this root m plus root n(i). And by the way, a, b, c, d are all real numbers. So by the complex conjugate law or something, I forgot what it's called. So basically, this is also a small tip. The reason why they always say, oh, a, b, c, d it has to be a real number is because they always provide like a complex root. And if both of these conditions are in the same question, you immediately know that the conjugate of this root is also the root of these 2 equations. So like it has to be, because or else you won't have real coefficients. So what happens is actually this detail matters a lot. So if you didn't like recognize this, I have no idea how you would do this question. So the next thing is we want to, by the way, this question you want to find what is m plus n. so the value of n plus n. So this question, what you want to do is you want to kind of see what you really have. And obviously, there are a lot of things that you don't have. So for example, you don't know the value of A, you don't know the value of B, you don't know the value of C or D. But what you know is there's something like one of the roots of these two equations. So what you want to do is you want to maximize the usage of this information. So how do we maximize it? One thing we notice is that in this equation, there's no x squared. There's no, the coefficient for x squared is 0. So immediately we know that we can use the Vieta's theorem. So Vieta's theorem, we just add all of those roots up, so sum of roots. And the reason why I said you have to recognize the conjugate is also a root is because the imaginary part, it straight up just gets eliminated. So we have 2m equals to 0. And m, immediately it's like 10. And that's it. Very convenient. How about the information? How much information can we get from this equation then? So obviously we know that it has a missing term x. So what we know is we use Vieta's theorem yet again, and we can do some algebra manipulation. So we times each of these roots together. And I'm going to skip the algebra part because it's very, very tedious. And at the end, what we get is, let's see. What we get is, so all the imaginary part cancels out. And what we get is, after solving the value of m, what we get is n equals to 320. So m plus n is 330. So that's it. Yeah, so at this question, the key is to recognize that in functions that have real coefficients, if they have a complex root, its conjugate also has to be a root as well. And also, Vieta's theorem is extremely important in mathematics competitions, and it's always used apparently. So our next problem is very, very interesting. So question 5. So this question is saying that there's this set called tau or something. I forgot what is the exact symbol. So tau is a set that contains all the obtuse triangle that has side length of 4 and 10. And so we assume that we assume that the area. Sorry, I'm trying to recall what the question exactly is. So we have tau s. So it actually has an argument. So the argument is the area of the triangle, and the set contains all the possible triangles that have this area s and the side length 4, 10. Actually, all the possible obtuse triangle. Yeah. So basically what happens is the question is asking for this range of values for the area, so A and B, inclusive of A and exclusive of B. It's very interesting because in this range of area, there's only one possible triangle, an obtuse triangle that satisfies the case. So I can give you guys a few moments to consider this question because it's a very valuable question. So for those who are able to solve it, congratulations, you're truly an excellent problem solver. And I'm just gonna show the solutions here anyway. So what happens is when we compute the area of a triangle, what we do is we actually don't really care about the angle. So let's say we have the base 4 and then 10. And this is an obtuse triangle, right? We care about the height. So another possible, as long as the height is the same, like we don't care how the triangle looks like. As long as the height is the same, the area is always the same. So if we have something like this, so the height is still the same, then although these two triangles look really, really different, what happens is, this is just the areas is always the same. So what we want to do is we want to find extreme cases where that couldn't be true. So I was actually looking at this question. I was wondering, how could there be extreme cases? So immediately I noticed that what if, for example, for this triangle, what if this triangle is a right angle triangle with 10 and 4 and h? So what happens if it's something like this? So another possible way to have a triangle that has the same area with side length 4 and 10 is something like this. And nothing else, actually. There's no way to construct another triangle that has, the same area. And this case is very special because in the first case, we have two obtuse triangle, actually. But what happens in this case is that we have one right angle triangle and one, obtuse triangle. So this is what we call like an extreme case where there's only, where like if h is like, slightly lower. So if it's slightly lower, then it will become an obtuse triangle. And this is actually the value of a. The value of h, the area of this triangle is actually the value of a. So let's compute this very quickly. Using Pythagoras, h is 100 minus 16, so 84, which is like 221. And another extreme case is this. So when 10 and 4 and I don't know what this is, 116 or something, but it doesn't really matter. And what happens is this triangle is very special because there's no other triangle that can have the same area. And this is why the area of this triangle is the value of b, because like this is not an obtuse triangle, so that's why it's exclusive. So the area of this triangle is, the area of a is 2 root 21 times 4 divided by 2, so 4 root 21. The area of this triangle is 20. So the question asks, what's the value of a squared plus b squared? So we have 4 root 21 squared plus 20 squared. So this is 16 times 21 plus 400. And it's like 736 or something. Let me just check really quickly. Yeah, 736. And that's question 5. Last question, I'm just gonna make a separate video on it because it's a little bit long. So see you guys in this next video.